Hello and welcome to the Dead Chemist Society. My name is Michael, and today we'll be going through the total synthesis of minus Finerenone. And this is some work that was performed by the Aggarwal group and was published this year in Angewandte Chemie. As of mid-November, this paper hasn't received page numbers yet, but I'll make sure to put a link in the description for the actual article. And this is the structure of the compound that they are synthesizing in this paper. It's conducted via an enantioselective 6-step synthesis, as we can see I've written here. And it has this rather particular naphthyridine core. Furthermore, this compound is actually really interesting because the reason why the Aggarwal group decided on actually synthesizing it is that it's a phase 3 candidate for treatment of chronic kidney disease, which is something that type 2 diabetes patients often suffer from. So they actually produced this compound on a rather large scale in this paper. And their synthesis starts out with this pyridone starting material. And the first step is a selective alkylation on the oxygen using silver carbonate. Next, they protect the free amine with pivenyl chloride to form this protected amine as an amide. So if you're wondering why this selective alkylation only reacts on the oxygen, I'll show you here how it works. So the pyridone is in a constant equilibrium with this aromatic stereoisomer. But interestingly, if you use silver carbonate, which is a fairly soluble base in organic solvents, you're actually able to selectively deprotonate the hydroxyl group, and in this way selectively alkylate using, for instance, ethyl iodide. It could also be methyl iodide or any other strong electrophile. So pretty neat chemistry, and it works just fine. So the next step of the synthesis is this quite cool reaction, I think. So they use this TMEDA, which is typically an amine ligand, and then N-butyl lithium. This reaction involves lithiation on this particular position, and as we know, alkyl lithium reagents are strong nucleophiles and can react, for instance, with this aldehyde, which is essentially what forms this new bond right there, and this is of course the former aldehyde. And this type of chemistry, at least the first step with the lithiation, is known as a directed methylation and is something that is pretty important for synthetic organic chemistry. So what we see is that we have this butyl lithium, and saying directed methylation essentially means that you have some groups in your starting material that are capable of directing the lithium towards a certain position. And in this case, we have the ether and the amide that are both somewhat nucleophilic because they have lone pairs. I'm just going to draw them out here, which can attract this positively charged lithium ion. And in this way, we are able to get this lithiation where we exchange the hydrogen for a lithium and lose butane. And you may be wondering, why are we even bothered by using TMEDA? Because that must, of course, have some significance for this reaction. And there is actually a good reason for adding it, unsurprisingly. So if we look at the structure of TMEDA, it's this very strong ligand. And furthermore, it's a really strong lithium chelator. And the reason why this is very important is that butyl lithium is not just in existence as monomers in solution. In fact, many of these organometallic compounds form these clusters in solution. That's also true for Grignard reagents, for instance. So the reason why the formation of these clusters is a huge problem is that you actually end up deactivating the reagent because essentially the reagent is less accessible when it forms these clusters. And what TMEDA is capable of doing, as it is a strong lithium chelator, is essentially breaking these clusters into smaller species in solution, and these are a lot more basic and as a consequence also a lot more nucleophilic. So TMEDA is used for alkyl lithium reagents. In Grignard reactions you would typically see the addition of lithium chloride is quite often seen. Additives like TMEDA and lithium chloride are commonly referred to as cluster busters because they essentially break apart these oligomers in solution and create more reactive species. So let's move on. Here we go. So the next step of the synthesis is this deprotection of the p-valuable amide, and this is just a common amide hydrolysis under acidic conditions. They use hydrochloric acid and some heat, and in this way they get the desired amine back. The next step of the reaction was the reaction between this free amine and this beta-keto amide under use of this chiral catalyst, which is a phosphoric acid catalyst, and then some 4 angstrom molecular sieves to remove water during the reaction. And what's really interesting is that they actually get their desired product already now, this minus Finerenone. And you may be wondering why there's so many minutes left of this video, and I'll get to that point in a moment. But first, I'll be showing you how this reaction works because it's actually quite interesting. So let's just have a look here. And I'll make really sure to underline this is a plausible reaction mechanism because they don't investigate it in the paper, and I don't think that is really within the scope of this video either. So if we look at the phosphoric acid catalyst, we can see that this is indeed a chiral compound, as these two naphtylidine moieties are locked, because actually there are 2 protons, one here in the front and one here in the back. So one from this naphtylidine in the front and one here in the back. And these cannot rotate across each other around this bond because you simply get a steric clash here. So this is an example of atropisomers, where the rotation around a single bond is not possible, and that causes essentially a new stereogenic center. And this I've drawn here is the R isomer. So I would guess that this reaction takes place by initially a protonation of this alcohol to form this really strong leaving group, as we know, just plain water. By losing water, we get this really stable cation, because benzylic cations are extremely stable because they are resonance stabilized in the aromatic system, and in this case we actually have 2 aromatic rings to support this positive charge. And as soon as we have an ion pair of something that is non-chiral and a chiral anion, we will have essentially a chiral species in solution. And I hope you can accept that the chirality of this intermediate is going to be really important when the enol tautomer of the beta-keto amide, I've shown the equilibrium here, when that reacts, the chirality of this intermediate is really important because suddenly nucleophilic attack from one side or the other is going to be favored. And that is exactly what we see, because when this reacts as a nucleophile, there's going to be a certain prevalence of either attacking from the front side or the back side of this intermediate, depending on how this phosphoric acid catalyst prefers to coordinate to this cationic intermediate. And that's exactly what we see. We see the formation of a new stereocenter. And essentially what we lack now to get our final product is an imine formation between this carbonyl and this amine. And I've drawn it here as the enamine, but essentially this is also going to be in equilibrium with the imine intermediate. And this is the way they get their Finerenone product. So the question is, why is this movie still several minutes long? Because now they essentially have their final compound that they sought out to prepare. Well, the authors realize that this final compound was only obtained with a 15% enantiomeric excess. That is fairly low and far too low in regards to what the authors originally sought out to do. So instead, they decide on quitting this path. So the authors go one step back and instead of using a chiral phosphoric acid catalyst, they use this unchiral phosphoric acid catalyst instead, and get a complete racemic mixture of this compound. After obtaining this racemate, they oxidize this compound back to the aromatic compound using nitric acid. And I would suggest that those of you who are interested try to look up what in fact is the mechanism for this reaction when you use nitric acid as an oxidant. I think you may be positively surprised that it's fairly close to what we learn on a first year chemistry course in regards to functionalizing aromatic compounds. Anyways, so the authors actually have a really cool idea in mind. They are planning on going via a transfer hydrogenation towards this desired product. And I'll try to go through how they do it, because, spoiler alert, they are gonna succeed. And give you a little bit of an idea on how to design reactions like this. So the reaction they have in mind involves this starting material that I've simplified quite a lot. I hope you can live with that. And then this compound, which is known as a Hansch ester. And I'll try to write out the name. It's like this, I believe. Hansch ester, which is probably the most lavish use of consonants ever in a last name. And then this chiral phosphoric acid catalyst. And they hope that they'll be able to generate a stereogenic center, as we see here. And the way this works, I'll take you through it because this is a lot to take in, of course, is that they have various phosphoric acid catalysts with different R groups. And they figure out that when they use these 9 anthracene groups, that they actually get a higher degree of selectivity. So just imagine anthracene groups here. That is our catalyst, the Hansch ester you have here. And then we have our starting material. And then there's one more really important point that I need to point out. And I'd like to challenge you to pause the video and figure out this question I have here. Why is this naphthyridine compound in fact a mixture of diastereomers, in fact a pair of diastereomers? And why would we see it as 2 compounds in an NMR spectrum, for instance? Okay, so in fact, this naphthyridine starting material also is a pair of atropisomers around this bond, because the bond or the rotation around this bond in particular is not free at all. Because as we can see, I've just drawn out the substituents here, just to teach you a little. They are in the way whenever we want to rotate around this bond. You could imagine that this methoxy group would start hitting into this ethoxy group over here. So we have 2 different diastereomers or atropisomers, and they refer to this, and I will refer to this atropisomer as the R isomer, and this one as the S isomer. And essentially, all that matters is which way the methoxy group is pointing. If it points out towards us, it's the R isomer, and if it points into the plane, it's the S isomer. And more interestingly, as there is a barrier for this rotation, they actually figure out that these 2 atropisomers start interconverting at around 40 degrees Celsius. And that is a pretty interesting finding that I'll get back to. So how does this transfer hydrogenation in fact work? And this is also going to be a lot to take in, but I'll try to take you through it as best as I can. So I've simplified the phosphoric acid catalyst as this weird blob with a phosphoric acid part on it. Just remember that it's chiral and it's very big. Then we have the S atropisomer of the naphthyridine, and we have the Hansch ester over here. And the same over here on the right side, we have the Hansch ester, we have the same R phosphoric acid, and we have the other atropisomer of the naphthyridine. And this mechanistic investigation was performed by density functional theory, which is a strong computational method for investigating especially transition states in different organic reactions especially. So we can see here in this transition state that there is going to be an interaction between the amine here, or the pyridine-like nitrogen, and this acidic proton on the phosphoric acid catalyst. Likewise, we can easily see here that there's going to be an interaction between the phosphoric acid and the Hansch ester. And what's really interesting about the Hansch ester is that it's capable of donating an H- to something, or hydride ion we could refer to, which is always one of the important steps in these transfer hydrogenations. And we can see here why it's really important to consider that this is in fact a pair of atropisomers, because this is the transition state for the hydrogenation. And you could imagine that if the methoxy group was sitting in this position instead, that being the R isomer, we would have a steric clash between the Hansch ester and the methoxy group that would be in this position. But this is the transition state leading to their desired product using the R phosphoric acid catalyst and the S naphthyridine isomer. And the way this works is that the hydride is capable of doing a nucleophilic attack here, while the nitrogen is protonated by the phosphoric acid. The reprotonation of the phosphoric acid actually ends up forming an aromatic compound on the Hansch ester. You can try to draw it out if you want, but that is essentially how the Hansch ester functions as a essentially source of hydrogen. If we look at the other case over here, we can see that I've drawn out the R-naphthyridine atropisomer. And as you can see, this is located rather differently in space as opposed to the S isomer over here. And that is essentially due to a mismatched interaction. So we would refer to this over here as a matched stereochemical interplay between the reacting species, and this one over here is mismatched. But it's the same reaction taking place, and therefore the same mechanism more or less. We see this protonation steps, and we also see the hydride transfer. There is just one big difference, and that is that since this is a mismatched interaction, there's going to be more steric clash between the reacting species. And that actually turns out to be a difference of over 9 kilojoules per mole, which is quite a lot actually. So with this in mind, we know that the R diastereomer atropisomer of the naphthyridine is going to react a lot slower as the transition state is significantly higher. That is chemistry 101. But actually, if you don't heat this reaction, it stops at 50%. It stops when you have the conversion of this compound, because this one reacts so much slower. So what the authors do instead is heating the reaction a bit, and actually what they see is that when they carry out this reaction at 100 degrees, this transfer hydrogenation is not only fast, but so is the isomerization of the starting material. And in that way, they are able to constantly have a replenished source of the matched or the favored S atropisomer of the starting material, and therefore they form their desired product in an 82% yield, and perhaps more importantly, they end up forming it with in excess of 90% EE, depending on the conditions. So I think this is a pretty cool way of resetting the synthetic plan and actually ending up involving some pretty cool chemistry. I'm always very excited when I see a transfer hydrogenation in a total synthesis, because it's rather unusual to come across something like this. Anyways, I hope you enjoyed this video, and feel free to ask questions in the comment section, and I'll try as best as I can to respond to them, and otherwise feel free to have a discussion. Anyways, thanks for listening, thanks for watching the video, and have a good day.